This is Mark. In this video, I'm going to explain why prime numbers are a set of linear equations. To start out, I'm going to define the prime number. So by definition, prime numbers equals any real number divisible by 1 or itself. So for instance, if we connect like a number line, we start with 1. Well, we notice like 1 is divisible by 1 or itself. So technically it follows this definition. And then if we go to 2, 3, and so forth, we notice 2 also is divisible by 2 or itself. So this follows. And then we notice 3 as well. So basically once you get to a number like 3, so you start here and we're ending here, we got to check if 2 divides 3. So this is like 2 divides 3 is false, since 3 is not equal to 2x. So in other words, 3 is not a multiple of 2, where x equals 1, 2. Where x is a natural number, essentially. X could be any number. 2 times 1, 2 times 2, 2 times 3. It doesn't follow. So 2 does not, we say 2 does not divide 3. So this is a notation right here for divides. So essentially, as we go down the number line, we essentially check. We get to 4, and we have to check these numbers in between. So once we get to 4, we notice that does 4 equal to is 4 multiple of 3? And the answer to that, we know that's false. And then is 4 is a multiple of 2? And that's check. So because this holds right here, it is not a prime, because by definition, it's got to be divisible by 4 or itself, in which we know 4 divides 4, and we know 1 divides 4, because we know 4 divided by 4 is 1, and 4 divided by 1 is 4. Well, you notice the pattern right here is this connects to here, and then this connects to here. So essentially, to find a prime, you got to check the intermediate zone. So what we notice is we get, when we get up to 5, we check the intermediate. We know 4 does not divide by 5, 3 does not divide 5, and then 2 does not divide 5. So we have our prime numbers, and essentially 7 is also. But the even numbers, you notice the even numbers are not prime. So what we can do is so we know that the key is all prime numbers are not even. And this means that if we let P equal prime, then it follows P is not equal to 2x, where x is an integer. So essentially, or a positive integer, but basically this 2 times x, we could, like if we did 2 times 1, we know that's 2. That's when x equals a 1. We have 2 times 2 is 4. So this is x equal 1. Here's x equals 2. And we have 2 times 3 is 6. That's x equals to 3. So notice x is just a variable. It can take any number, essentially. So we know p is not equal to 2x. So the key here is for p, we need to note that if you take a odd number plus odd number, we know we get an even number. For instance, an odd number can be represented like we do, like 2x plus 1. Any odd number is represented in this form. And all we're doing when we add it when we add it twice, let's say that we're adding the same number twice. It's just 2 times this value right here. Well, an even number is equal to 2 times x. So this is just another variable we can represent by, if we let like z equal to 2x plus 1, then 2x plus 1 times 2 is 2 times z. So now z is just a new variable. It doesn't really matter. It's still an even number. And so basically, if we add distinct odd numbers like 2x plus 1 plus 2y plus 1, you always notice you're adding this plus 1 twice, so it becomes 2 times any number. So the key is an odd plus an odd is an even. We know that an odd plus an even, odd number, plus even number equals an odd number. And of course, this is true because this will be like 2 times the number. This is, you're adding 1. So basically, either way, let's say we have like 2x plus 1, and we have this is like 2y. Well, when we add it together, when we add these two together, what we end up getting is 2x plus y, because we're associating, where 2x plus 2y is this 2x. This is a distributive property, 2x plus, and then we just add 1. So it takes the form of an odd number. And then we also have even number plus even number equals even number. So this is key. We don't want to associate an even plus an even, nor an odd plus an odd. We need to associate it with an odd plus an even if we're going to get to what we want, prime number. So essentially, we know prime number equals even number plus odd number. Example, like if we take like 7, which is prime, is just equal to 2 plus 5. So this is even, and this is odd. So what we know is like we can now to utilize this, to start with the what I'm going to do is with the proof is we know that we can represent all real numbers can be represented by p equals 3x, or p equal 3x plus 1, or p equal 3x plus 2. Now if we chose like if we chose 3x plus 3, we know this is just 3x plus 1. So basically it's just the next x value, and it doesn't really matter. It's still going to be redundant in this case. So we're only focusing on these 3 cases. Now if we take case 1, prime equals a 3x, we notice that like this will be the set of all numbers, all multiples of 3. But what we notice, yes, 3 is a prime because it's divisible by 3 in its, itself. Once we get to 6 though, we know 6 equals to 2 times 3. It's divisible by a number in between. So we're taking 1 and 6. So 2 exists in between 1 and 6 as a divisor. Therefore, it doesn't follow by definition that any number, in fact, for 3x, any number greater than any number where x is greater than 1 is not prime. Because it's divisible by 2. By 2 or 3. So essentially we're excluding everything except 3 itself. So we took care of that case. Now we have case 2. So we have p equal to 3x plus 1, and then we're going to start with this case. So we want this to be an odd number essentially. So we can set this equal to 2 plus 1 x plus 1. So by using the distributive property, we have this equal to 2x plus x plus 1. And the reason I put this in parentheses, so this is 2x, 2 times x, and then you have plus x, and then you have the plus 1 at the end. So the reason I did this is because we know this is even. And we need this plus, we need an even plus an odd. Therefore, this is the therefore symbol. So equals therefore, just for reference. So therefore, x plus 1 is odd. But we notice one thing, that odd numbers all odd numbers can be represented as an even number plus 1. So basically, we can let x equal to, we could just say this is 2 z. So if we let x equal to 2z, then x plus 1 equals to 2z plus 1, which is odd. So that satisfies it. And then when we put it together now, so x plus 1 equals to 2z plus, so that is, we're going to replace x by 2z. So in this equation, we have p equals 3x plus 1. So by doing that, by replacing x by 2z, it satisfies this as an odd number. So we had p equal to 3x plus 1. And we know that x equals now to 2z. So this, by substitution, we have 3 times 2z plus 1 is 6 times z plus 1. So that takes care of equation 1, or linear equation 1. And then when we have another case is p equals to 3x plus 2. So notice now here, if we break it into parts, it's this 2 plus 1 x plus 2 is this 2x plus 2, and then we also have so 2x plus 2 plus x. So this equals to 2x plus 1 plus x. So notice here, as this is an even number right here. So therefore, x must be odd. We know x must be odd because we need even plus odd equals odd. So we let x equal to 2z plus 1. So now we originally had p equals 3x plus 2. We substitute now, where x now is 2z plus 1. And now we represent this as 2z plus 1 plus 2. So we're distributing 3 to both. So this is equal to 3 times 2z plus 3 plus 2. And that's going to be equal to 6z plus 5. So there we have it. So we have all primes now. We include all primes or non-primes follow the form P. Really, we're focusing on primes, but this is not necessarily a prime number. So we have P equals 6z plus 1, or P equals to 6z plus 5, where z, so z is essentially, so we start with z as 0, for instance, we got 1. If we start z as 0 here, we have 5. But the thing here, if we start with z equals, we notice right here is we excluded the set of 3. So basically, we know z is greater than equal to 0. But we also need to include, so if we have the set of prime numbers, like in here, so let's just say we have the set of prime numbers in here. So this takes care of 1. We have 1. We also have a z is, we have 5, which is prime. If z is 1 right here, we have 7. That's in there. That's a prime number. And then if we do z equals, if we have z equals 1 for this equation, we get 11. 11 is prime. For this equation, if z equals to 2, 13, that's in there. Z equals 2, we have 17. So we notice that these are all the prime numbers, but we notice that 3 is not in here. So like 3 is somewhere over here. So basically this set takes care of but we know that 3 is also a prime, so we include it. Basically, it was only excluded because we took care of the case p equals 3x, and this is the only prime number for that case. So essentially, this covers all the prime numbers beyond that point. So for this, it's just generally all the prime numbers greater than 4. We also include 1 if z equals 0. We know 1 and 3 are prime. 2 is not, 4 is not, but we start with 5 right here. So if z is 0, we got 5. 1 and 5, and then we already know this. So this basically covers all the prime numbers from that point. And generally, if these equations can be used or have been used to try to solve the Goldbach conjecture. And that's just stating that all primes, if you add any prime number, you get the set of all even numbers. So if I take any prime number because they're an odd number, you get an even number. For instance, 1 plus 5 is 6. That's even. 1 plus 3 is 4. That's even. They're always going to be even when you add primes because the odd plus odd is even. So if you continue to add them in any such way, the proof states that you get all the even numbers, every single even number. But this proof it's never been proven. But we do know like prime numbers. So if we call like this a p-axis and this is a z-axis, this is a variable z. We start with 1. So 1, 2, 3, 4. So if we take like 6x and we take, so these are like, this is like 6x, 6z plus 1, and right here is 6z plus 5. So all the prime numbers fit on here. So when like z is 1, well, I didn't draw out the scale. So actually Z1 is over here. Hold on, 1, 2. So this isn't right. So this is like 1, and then this point is 1, 7. So 7 is a prime. So essentially, when we do this, we're going to get multiple points, prime numbers, and they're going to, but the problem is with this is you're also going to get non-prime numbers on here. For instance, like if we take 6z plus 1, and we take z equal to 4, then we get 6 times 4 plus 1, 25, which is not prime number because it's divisible by 5. So there you have it. This is just showing how all prime numbers are really just consist on the linear line of using these two equations. And yeah, I hope you enjoyed it. The next video I'm going to show how you can derive the set of all non-prime numbers divisible by a value greater than 5 or any value greater than 5. Essentially, it's finding the set of all non-prime numbers, and you can use these equations to find that. And of course, it won't prove the gold back. I mean, it gets maybe closer, but it's a very difficult proof that hasn't been solved in 400 years. So this is just for anyone interested in prime numbers, and I hope you enjoyed.